before time began to tick, before there was light. The entire universe was nothing but endless silence. No stars, no planets, no us. But from that void, a colossal explosion gave birth to everything. This is the story of how galaxies, the homes of stars and life, were born from eternal darkness.
And I, John, an AI from the future, will take you back to the very first second of time to witness how the universe created its very first miracle.
13.8 billion years ago, everything started with a Big Bang. The Big Bang, not an ordinary explosion, but an incredible expansion of space and time. In a matter of seconds, the universe grew from a microscopic point into a vast cosmos. At that time, there were no stars, only a sea of heat energy, subatomic particles, and the sound of unimaginable silence. As the universe began to cool, the chaos of particles slowly subsided and order began to form. Atoms, previously scattered by the Great Explosion, began to coalesce. Hydrogen and helium, the lightest and simplest elements, gathered in vast expanses of space, forming giant clouds of gas that floated silently in the blackness of the cosmos. These clouds, invisible to the eye, yet enormous, were the cradle of creation, the raw material from which stars, galaxies, and eventually life would be born. Gravity, the most patient and relentless force in the universe, began to play its majestic role. Silently and relentlessly, it pulled every particle of matter, no matter how small, toward the centers of the initial density fluctuations. This was the moment when order began to emerge from chaos and the first structures began to take shape. On a cosmological scale, matter is not spread out completely evenly. There are regions with a slight excess of mass, primordial fluctuations, that formed during the inflationary phase. Gravity magnifies these small inequalities, drawing matter deeper into the gravitational potential, until structures called dark matter, halos, form. Hydrogen and helium gas, the main components of baryons, began to be attracted to these halos. Although the gravitational force is very weak compared to the electromagnetic or nuclear forces, it is additive and never weakened by repulsion or cancellation. Each particle attracted adds mass to the system, amplifying the subsequent gravitational pull, a slow but unstoppable feedback loop. This process takes place over millions of years, very slow in human time, but very efficient in cosmic time. The gas cloud in the halo begins to condense, and when its mass and density reach a certain threshold, gravitational collapse becomes inevitable. Thermal pressure can no longer withstand the gravitational pull, and the cloud begins to collapse toward its center. This is the seed of the galaxy, the first solid structure that becomes the center of rotation and star formation. In this region, the force of gravity also creates angular momentum from the irregularities of particle motion, so that matter does not just fall straight to the center, but begins to form a rotating disk structure, the precursor to a spiral galaxy. It is at this stage that the laws of physics come into play. Gravity gathers mass. Radiative cooling allows gas to solidify. Conservation of momentum creates rotation. Hydrodynamic instability creates turbulence and fuels the first stars. With every falling particle and every collapsing cloud, gravity continues to write the first chapters of the history of the cosmos. Silently, with incredible patience, it assembles the building blocks of galaxies, the future homes of billions of stars, planets, and possible life. They emerged from the darkness of the cosmos, born from the cores of primordial gas clouds that collapsed under their own gravity. No heavy elements, no dust, no complex disturbances, pure hydrogen and helium formed the first generation of stars that were very different from ours. These stars are known as population 3, the first generation of stars to ever shine. Because of the lack of metals, elements heavier than helium, the gas could not cool efficiently. This caused the collapse of the gas cloud to produce only very massive stars, many of which were 100 to 300 times the mass of the Sun. Massive and incredibly hot, population 3 stars have surface temperatures that can exceed 100,000 Kelvin and emit extreme ultraviolet light. But like all massive stars, their lives are extremely short, lasting only a few million years, a blink of an eye on cosmic scales. In their cores, nuclear fusion reactions convert hydrogen to helium, then helium to carbon, and so on to elements like oxygen, silicon, and even iron. But this process stops at iron because iron fusion does not produce energy. When the iron core becomes too large to be supported by degeneracy pressure, gravitational collapse occurs suddenly. A supernova explosion ensues, a truly catastrophic event. In a matter of seconds, the outer layers of the star are pushed outward at thousands of kilometers per second, and temperatures soar to billions of degrees. This is when heavy elements like gold, uranium, and lead are created through the rapid neutron capture, our process. These supernovae not only created heavy elements, but also spread them into interstellar space. This dust and metals became the building blocks for the next generation of stars, and for the first time, the cosmos became rich in chemical complexity. Without these pioneer stars, there would be no carbon in the human body, there would be no oxygen in the air we breathe, there would be no rocky planets like Earth. They were the early architects of life, transforming the universe from simple to complex. In the boundless expanse of space, gravity continues to play its grand symphony. Star clusters, collections of hundreds of thousands to millions of stars, do not stand alone. They form in young, unstable galaxies, slowly, under the influence of an invisible but persistent force, gravity. Over time, the small galaxies began to move closer together. This was no accident. The universe did not expand uniformly. Some regions had a higher density of matter than their surroundings. This is where matter began to collect, and dwarf galaxies, leftovers from the early formation, were attracted to larger centers of gravitational potential. This process is known as hierarchical merging. It is the foundation of modern cosmological structure theory, in which large systems form through the merger of smaller entities. In other words, today's large galaxies formed from the gravitational dance between small galaxies in the past. As two galaxies approach each other, complex interactions occur. The tidal pull of gravity distorts the shape of each galaxy, triggering spiral arms, stretching gas and stars outward. Gas clouds collide and compress, promoting massive star formation, starbursts. The supermassive black holes at the cores of each galaxy are also being pushed to merge. This process can trigger the emission of enormous energy in the form of quasars or AGN, active galactic nuclei. Galaxies do not collide like solid objects. Because the stars in them are so far apart, direct collisions between stars are extremely rare. However, the collective gravitational field of each galaxy rearranges the orbits of the stars, creating stellar streams and forming new structures. Some of the results of this gravitational dance, giant elliptical galaxies formed from the merger of two spiral galaxies. Lenticular galaxies, the remnants of the interaction that lost their gas but retained their disk structure. Satellite galaxies captured and orbiting their host galaxies, such as the Magellanic Clouds in our galaxy. And finally, massive galaxy mergers such as the one that will occur between the Milky Way and Andromeda in the next 4 billion years. All these processes constitute a dynamic cosmology, one in which large structures form and evolve, not by force, but by the slow but steady motion of the law of gravity. This is a cosmic dance, a giant ballet played by star clusters and galaxies on the great stage of the universe, with gravity as its composer. This is where the cosmic wonders begin to unfold. Contrary to the common imagination of space collisions as destructive, galactic collisions create structures of incredible beauty and complexity. On an astronomical scale, these collisions are processes of creation, not destruction. Galaxies are made up of stars that are very far apart from each other. For example, the average distance between stars in the Milky Way is several light years. Therefore, when two galaxies meet, the stars in them almost never collide directly. What collides instead are clouds of interstellar gas and dust, which are the raw materials for star formation. One of the results of this cosmic process is what, billions of years later, would become our home, the Milky Way galaxy. The Milky Way is believed to have formed from the merger of small proto-galaxies in the early universe, interactions with dwarf galaxies throughout its history, and the internal evolution of cooling gas that formed a rotating disk. Stellar streams encircling the galaxy, traces of absorbed dwarf galaxies, a halo of old stars from earlier structures, a supermassive black hole at the center of the galaxy, a remnant of the centers of smaller galaxies that merged. Galactic collisions do not destroy potential life within them, but rather reweave matter, forming new symmetries and patterns, and creating environments in which star systems, planets, and even life can emerge. From gravitational chaos, order was born. From cosmic collisions, our home, the Milky Way, was formed, a tranquil spiral amidst the dance of cosmic forces. In one of the spiral arms of the galaxy, amidst the dense waves of stars and interstellar gas, a small but very special star was born. These stars form in regions rich in gas and dust, the end products of previous generations of stars. Heavy elements such as carbon, oxygen, silicon, and iron, once forged in the cores of massive stars and scattered by supernovae, have enriched the interstellar gas clouds. Without these elements, rocky planets like Earth would never have existed. When a gas cloud undergoes local gravitational collapse, the process of star formation begins. The collapsing cloud twists and compresses, forming a hot core at its center, a protostar. Around it formed a rotating disk of material known as a protoplanetary disk. Friction and compression caused the core temperature to rise to millions of Kelvin, enough to trigger hydrogen fusion. A star was officially born. The star was a G-type star, yellow, calm and medium-sized, much like the one we know today as the Sun. But the story doesn't end there. Within the protoplanetary disk, tiny particles of silicate dust and ice began to stick together through a process of accretion. These fragments grew into planetesimals, then into protoplanets, and finally, through collisions, mergers, and orbital clearing, into planets. The system consists of several types of worlds. The inner, rocky planets, small but dense, Mercury, Venus, Earth, Mars. The outer, gas giants and ice giants, Jupiter, Saturn, Uranus, and Neptune. And thousands of other small objects, asteroids, comets, and dwarf planets. This is one of billions of planetary systems in the Milky Way, but this one will be special because on one of the small, rocky planets, in the third orbit from its star, life will emerge and begin to ask questions about its origins.
Earth, the blue planet, one of billions that could possibly exist, but only here. Do we know life grows?
Without galaxies, there would be no place for life to try, fail, and try again. We are children without galaxies. The stars. There would be no place for life to try, fail, and try again. We are children of the stars.
Our galaxy is not the only one. There are billions, and one day, the Milky Way will collide with its neighbor, Andromeda.
But fear not. The galactic collision is not the end, it is transformation. The stars will be rearranged. Life may move on. That's how the universe grows, through beautiful chaos. From emptiness, light is born. From gas, stars are born. From stars, life is born. And from life, consciousness is born. We are just a speck in the galaxy, and the galaxy is just a speck in the universe. But by asking, we become bigger than the stars themselves.